Hello everyone, welcome to our new tutorial video for the continuation of solving problems of thermodynamics. Here we continue. As we proceed to the second law of thermodynamics, so now we are applying the question where the first law and second law of thermodynamics can be used to solve. So this is a conceptual question where the conceptual understanding of first law and second law of thermodynamics can be applied in analyzing this kind of problems. So here we go. Let's read the question. If a closed system experiences a net work transfer while it undergoes a reversible process, does a net heat transfer from the system always occur? If not, please provide an example when a net heat transfer occurs and another when it does not occur. So that is the question. So here we have some note to take. As we have seen, they say the process is reversible, meaning what? And then a net work transfer, so meaning the work transfer cannot be zero, it's always occur as per the question. So what we are going to analyze is the heat transfer, whether it can occur or not, and then if not, then we provide an example on which heat can occur and which heat cannot occur. So after that we'll just give two examples of them and we call it a day. So let's start with solution, as we always proceed with solution. So we are starting with solution. So we are starting with solution now. So since we have seen that the system is closed, so we have a kind of closed system. So system is closed from the question. Then state, we don't have to mention the state since we have not given the state, so we'll assume the initial state, T1 initial state and T2 final state. Then interaction, that's the procedure of solving problem with thermodynamics. So work transfer is not equal to 0. Our task is to see whether the value of heat can occur. So that is the interaction, and then we have given that the process is reversible. So we know a reversible process, there will be no entropy generation, so entropy is not generated, so therefore S gen is equal to 0. So S10 is equal to 0. So now we try second law of thermodynamics and see. So change in entropy is equal to the entropy transfer plus the entropy generation. So this entropy generation is 0. So entropy, change in entropy is equal to the entropy transfer, which is equal to the integral from 2 to to 1 dq from 1 to 2 all over the constant temperature. So entropy transfer, as we see, is not equal to 0. Entropy transfer is not equal to 0. So this means that ds is equal to, by integration, q from 1 to 2 all over the temperature. So q is equal to T ds. So therefore the value of q depends on the change in entropy, which is not equal to 0, and the constant temperature. So heat may occur or it cannot occur. It depends on the entropy. If entropy is 0, heat cannot occur. If entropy is not equal to 0, heat will occur. So therefore we can say heat transfer can occur, but not always. It only depends on change in entropy. So that is it. So then they ask us to give example when heat transfer occur and when heat transfer is not to occur. So now let's give two example. So now example. So when heat transfer cannot occur, so number 1, we have isothermal process. Isothermal change or process. So in isothermal process, heat is not to occur. So let's analyze. Let's show that what we analyze is true, or what we have given is true. So analysis. So T1 for isothermal process is equal to T2. T1 is equal to T2. Since isothermal mean no temperature change. So now we apply the expression, that is the change in entropy, is equal to mc ln T2 over T1. So T2 is equal to T1 from the given expression, so meaning this bracket is 1, so therefore ln 1 is 0, so meaning the change in entropy is 0. So from what we have analyzed, we see we said if entropy is 0, then heat transfer is not to occur, is 0, that is equal to T ds. So we can substitute by doing this. This shows that we have T into 0, which is 0, that is Q is 0, hence heat transfer cannot occur in isothermal process. So let's give another example under this. Then Roman 2. So Roman 2, we have adiabatic process. Adiabatic process. So we do the same analysis. In adiabatic process, what we mean by adiabatic process is that adiabatic process is a kind of process whereby there is no heat transfer into or out of the system, like isolated system. So if that is the case, heat transfer is equal to 0 automatically. So if heat transfer is 0, meaning there is no heat transfer, so heat transfer is 0. So heat transfer is 0. So meaning what? Heat cannot occur, or we can apply the tax, that is Q from 1 to 2 is equal to T ds. So if heat is 0, then what is ds? ds will be 0. So therefore heat transfer cannot occur. So heat transfer cannot occur. Then we'll give an example in which heat occur. So B, example when heat transfer occur, or you can say can occur. So A, Roman 1, we have isobolomeric. That is a process whereby the volume is constant, so there is no change in volume. So dB is equal to 0, no change in volume. So now we analyze. So work is equal to the integral from 2 to 1 in what? For constant volume process, that is P dB. So dB is 0, meaning what? Work is 0. So work is 0. Now we apply the first law of thermodynamics. We try the first law, that is change in energy is equal to work, is equal to minus the work net. So heat transfer is equal to the change in energy. So change in energy is not equal to 0 in isobolomeric. So heat can occur. So heat can occur. Then B, so B, we give example when heat can occur. Heat can occur. So Roman 1, we said isovolumeric. That is a process whereby the volume is constant. So we analyze using the second law of thermodynamics. So we try Peirce law. So dE is equal to then plus minus work net. So as we see it, they say dE is equal to du if assume the system is stationary, that is the change in potential area and kinetic energy are 0, which is equal to mc into theta 2 minus theta 1. So in this case, theta 2 is not equal to theta 1 since the process is isovolumeric. Only B1 is equal to B2. So meaning what? dE is not equal to 0. So if dE is equal to 0, then heat transfer is not equal to 0 from this equation. So therefore heat transfer can occur. So heat transfer can occur. That is analysis. Then example 2, we say isobaric, or we call it isochoric. They are all the same. Isobaric process. So in isobaric process, the pressure is constant. The pressure is constant. So work done, that is the change in pressure, is 0. P1 is equal to P2. So work done is equal to integral of P dV. So we try Peirce law of thermodynamics again. So by doing this, dE is what? So still dE is equal to mc into theta 2 minus theta 1. So dE is not equal to 0 since temperature is not constant. So therefore Q is not equal to 0. So there is heat transfer. So therefore heat transfer occur. So that is it. Thank you very much for listening.